So in our problem solving ways, we come up with method 2. Method 2, we used 50mm thick boards by 150. We cut a back cut in, leaving about 25mm hinge, and then set it up in the jig, anchoring it below in the stump, anchoring it above with the brake test device, and then breaking that off again with a low elongation rope with a load cell. That also didn't work as well as we'd like because it tended to tear more out of the front. So we then went to the third method, which was to put a small 4mm crease in the front of our wood, shorten this up so we were still left with 25mm hinge, and then we were able to break it off and not have undue breakage on what was meant to be the hinge or wood pulling out from a sawn surface. So all of a sudden we started to have more consistent breaks that we could probably measure. The problem was that I was using boards of 4.2 metres long, and so with the length of these boards up here, they then started to torque at the point of break once they'd started to move, and interfered with our load cell readings. It was also much harder to define where the actual angle of failure was. So, method 4, we shortened out our sample sizes to have 1 or 2 samples per board, and that made them much shorter where they had little or no effect of torque on our results. I've drawn up a very brief diagram of the problem of having these samples too long. So once they come over a certain distance, gravity would take over and start assisting the weight and decreasing the load on our load cell. While it was moving, it has kinetic energy. Obviously that's the same as a tree once it gets moving, but we're looking to measure accurately these angles and the load. So we needed to narrow that down to get some consistency. So kinetic energy and the gravity assist was overcome by shortening these boards down. We were able to get more accurate loads and angle of failure. So we thought we were getting closer. Let's have a look at how that worked out. So capturing the data became a real problem, became increasingly difficult the more errors that I found. In the red system, this is how we pulled the sample. So we've got our sample set up here, bird's eye view. We would have a low elongation rope, load cell, low elongation rope to the excavator, which would gently pull it off. And that way we could Bluetooth the results to our phone and have a reading or graph of what had occurred from when we'd hit the start button. Prior to starting that, we'd start the camera rolling, and that was getting at 500 frames a second, and we would then be able to observe the break occurring. As I said, we used a pendulum on the actual device to start with, and that proved to be a joke. One of my friends, Kieran, came along and said, why don't you use this KineV program? He installed it for me, showed me how to use it, and we were able to digitize or biomechanically look at what had occurred up here and try and align the load cell with that camera. Method 1 didn't work, simple as that. And we started improving method 2, 3 and 4. I'm going to pick up the improvements across each part of it as we go. The first of it is when we fix the sample to the stump. The stump I selected in the area out there, I cut a slot through the stump, and that enabled me to slide the 25mm thick sample in there, and then I wedged it to hold it in place and then would break it off. The problem was that even this part of the stump was flexing with the load. So it's a great indicator for, as the tree departs, the timber flexes in that hinge. And I had trouble containing that so that the actual sample was tight in the wedges that I'd placed there. I tried putting straps around the stump and it still happened. So I cut it off here and wound up with a separate block that was mobile. I then used the straps to ratchet it in, the 2-ton ratchet straps, and that pulled it in tight against the sample. Some of the problems I had was the sample was only so thick compared to the stump, and given that the ratchet straps were pulling on the sides, it tended to want to roll around, so it was a pain in the neck to strap. I then progressed to chains and over-centre dogs. So I wound up with chains around here with an over-centre dog and one across the bottom of it. That started to hold the block and the sample in place a lot better. I still could observe flecks in the camera and gaps appearing where the sample was under load. By cutting a piece off the bottom of it, I then had a mobile block. I could actually increment a 25mm step, a 50mm step and a 75mm step. The back cut would be level with what is the flat top of the stump, and the scarf could be made to be level with wherever I position that block. It also meant I could take it up 25mm and do a minus 25. So all of a sudden, by having this block mobile, I could actually fix a hard edge of timber against my sample for whatever I was testing. And I still noticed flex. To measure the changes in load and the high load, I used a Rock Exotica. I did have a lot of problems with the Rock Exotica, the Enforcer. Yeah, the Bluetooth kept dropping out when I least wanted it to, or when I didn't see it. Human error, my mistakes. Sometimes I wouldn't put it onto fast sample, or I wouldn't record the maximum load, which is important. Otherwise, for what I was doing at the time, it was a good device. And if we have a closer look at them, we can measure the force in kilonewtons, pounds or kilograms. You can, it'll record the max if you turn it on. So at the moment it says max in the bottom left. So it'll record the maximum load on the cell during the test. The sample can be either fast or slow. You can change it to 2 samples per second, or fast, which is 500 samples a second. So measuring the angle. A critical part of what I wanted to do was measure angle of failure. With my camera I had a 5D Mark II, so I had a lot of firepower in the camera. What I did was set the camera up exactly at profile at the pivot point where the sample was being broken. This is our sample, there's our stump. Action to the side. What it meant is that I had to choose an artificial horizontal for the program and a sharp edge on the back of our sample And this program would monitor and read out all the angle changes right through the breaking process, even after it left the stump. So it was an extremely good way of doing it, and 500 readings per second. And so this was the business. I could then accurately read angles. We'll look at it in due course, but on top of reading the angles, it gave us angular velocities, angular accelerations. It would give me graphs and obviously the Excel spreadsheet for all that data. So all of a sudden, I had a huge amount of data. The next thing on my progression was aligning the load cell and the computer program looking at the angles. That became a problem. To get the timing of the start of the load happening, to get the high load accurate, and the camera, we had to somehow sync that. And if you know the clapper boards for filming, they clap it, the sound and the actual closing of that align a separate soundtrack to the actual film. So what I started off trying to do that, but of course that wasn't working. I would then get hold of our rope here, pull down and give a sharp jerk. That would give an impulse on the graph for the load cell. So on our graph, there would be a spike at the start before it started, and the camera would observe how far the top of it came forward. At the most furthest point forward, that aligned perfectly with our spike. So then I had a way of aligning the camera data with our load cell data. The last thing I had to deal with was sample variation. I thought boards coming from the same tree, the same board, would have a great consistency. There was a large amount of variation. Often the grain, especially in the pine, it ran all over the place. But there was knots and there was defect in the timber, and these needed to be taken into account when we started comparing angles of break and the load being applied. So it suggests that we need a high sample number for it to be a valid experiment.